By the time we're done with this lab on buffers, you are going to be a buffer master. You'll know everything there is to know about acid-base buffers. The purpose of this lab is to create a buffer at a target pH. And so I will give each group a target pH, and ours is going to start with 5. So what if I want to make a buffer with a pH of 5? So a solution that'll hold a constant pH of 5. All right, so first we have to determine which acid and conjugate base pair we should use and give an explanation for our choice. So we have 3 choices of conjugate acid-base pairs that we can use to create our buffers in this lab. One option is acetic acid. And the acetate ion, which would come from a sodium acetate compound. We can make a buffer with citric acid. And its conjugate base would come from sodium citrate. Or I can use carbonic acid. And then its conjugate base would come from sodium bicarbonate. Okay, so here are the 3 choices. Now, on the front side of this lab sheet, we're also given Ka values for these acids. And so one of the best ways of starting off this is to say, let's look at the Henderson-Hasselbalch equation. It's pH equals pKa plus the log of this ratio, where it's the concentration of the negative ion, the conjugate base in this case, over the concentration of the original weak acid. Now remember that pKa just means opposite log of the Ka value, and they'll give me all of that information in the equation packet. All right, so I see a table on the front side that gives me Ka values, which is fantastic. And so if I had a 1-to-1 ratio of weak acid to conjugate base, remember how we said then that if you had a 1-to-1 ratio, if this was 1/1, the log of 1 is 0, and then the pH would just be calculated as opposite log of the Ka. If you had a 1-to-1 ratio of your weak acid and conjugate base, it's a good place to start. Let's say we had a 1-to-1 ratio. Then if I go opposite log of the Ka for these 3 weak acids, where would I be at? What would I get for a pH? So let's try that. If I look at the acetic acid, I'd say pH would be opposite log of the Ka, which is 1.8 times 10 to the negative 5th. All right, so my pH then would be, if I plug this in my calculator, I'd be looking at about 4.74. All right. Then my next option is a citric acid buffer, where I would have citric acid solution. And then if I look at the materials list, we would have sodium dihydrogen citrate, which isn't a real big deal. The key is just that it would only have 1 hydrogen removed from the original acid. We call this a triprotic acid, meaning that if I look at the initial formula for citric acid under the materials list, it has 3 possible hydrogen it can donate. And so if I donate just 1 hydrogen, we would be left with this dihydrogen citrate ion, which would come from the first dissociation or the first hydrogen released. Why do I care? Because if I look at this table of Ka values, for citric acid, they give me Ka1, Ka2, Ka3. I could release 3 hydrogen ions. Well, the version of the conjugate base that we would use would be the base formed after just the release of 1 hydrogen. So I'm going to use Ka1. Now, not very often do we work with these acids that have more than 1 hydrogen. Obviously, we can. But then you would see multiple Ka values, and they just represent the release of each successive hydrogen. And so I'm going to use pH is opposite log of the Ka1, 7.4 times 10 to the negative 4. So we'll plug that in our calculator, and I get a pH of about 3.13. Alrighty. And the last one, carbonic acid. If I look in the materials list, carbonic acid is going to be listed as seltzer water, or H2CO3. It's called a diprotic acid. It has 2 hydrogen. Well, that's why in the acid dissociation table, you've got Ka1 and Ka2. There's an equilibrium constant for the first hydrogen, and then there's another constant for the release of the second hydrogen. Well, the solid conjugate base that I'm using in the materials list is sodium bicarbonate. Well, the sodium is a spectator, but then I have hydrogen carbonate or bicarbonate, which means then that it's just the release of 1 hydrogen from the original acid. Again, why do I really care? Just because then I'm going to use the Ka1. So to calculate my pH, I'll just say opposite log of Ka1 for the carbonic acid, 4.3 times 10 to the negative 7. And we'll plug that in and get about 6.37. Okay, so these would all be assuming that I had a 1-to-1 ratio of acid and conjugate base, then this would be the pH of the resulting buffer. Well, I want a buffer with a pH of 5, which means that if we at least start with the pH here that's closest to 5, I can tweak that ratio of conjugate acid and I should say conjugate base and weak acid, but I at least want to start with a pH that's close to my target if I had the 1-to-1 ratio. So in that case, if I want a solution with a pH of 5, closest is going to be the acetic acid buffer. So I'm going to say that I'm going to choose the acetic acid buffer. And when it says to give an explanation, I would maybe just write a sentence that says, with a 1-to-1 ratio of acid and conjugate base, my pH is 4.74, which is pretty close to the target. Now, I want the target pH to be a little bit higher or a little bit more basic. So in the end, I'm not going to use a 1-to-1 ratio. I'm going to use a ratio that's a little bit higher in the conjugate base than the original weak acid. Fantastic. But we're at least going to start close. This could even be like a multiple choice question where just look at the exponent of 10 and they wouldn't give me anything in a multiple choice question that I couldn't just estimate without a calculator. Where, I mean, the acetic acid, my pH would be probably close to a 5. The citric acid, I don't know, somewhere around a 4. The carbonic acid, probably somewhere around a 7. Or at least then I can pick the acid conjugate base combo that would get me closest to my target just by kind of estimating, looking at the exponent of 10 from my Ka. Okay, so now we have to do some calculations. We want to know how many moles of the solid conjugate base should be added to a liter of the weak acid solution to produce our target buffer. Okay, so all of the conjugate bases are solids. Sodium acetate, sodium dihydrogen citrate, or sodium bicarbonate. they're all going to be solids. And eventually, if we can figure out how many moles to use, we can change moles to grams. And then we can measure grams of our solid. So let's take the Henderson-Hasselbalch equation and plug in what we know. Okay, so I know that I want the target pH to be 5. So I'm going to start there. pH is going to be 5. That equals opposite log of my Ka, 1.8 times 10 to the negative 5th, plus the log of this ratio. Now, I don't know how much of this solid conjugate base I should use. So for this ratio, I'm just going to say on the top, it's going to be the concentration or molarity of that A minus. We'll just call it A minus. It's going to be the acetate ion in our example. Then on the bottom, if I look in the materials list, I'm going to use acetic acid. And it lists it as a 0.1 molar solution. So on the bottom, this is going to be like 0.1 molar HA. And so they're telling me the concentration of the acid that's already in solution, that'll be 0.1 molar. And then I want to know how much base. What's that concentration of the conjugate base? All right, so let's simplify this the best we can. I already know that opposite log of the Ka is 4.74. So if I subtract that on both sides, I'll take 5 minus 4.74, and I have 0.26 equals the log of this big ratio. So it's A minus all over 0.1 molar HA. Okay, let's see if we can simplify this a little bit better. If I want to get rid of the log, these are logs base 10. So I could just take this 0.26 and put it up there as the exponent of 10, right? And so I could say then that 10 to the 0.26 equals this ratio. A minus all over 0.1 molar HA, which again, it'll be our acetic acid, but it's just a lot easier to write HA than hydrogen acetate. All right, so the log is the exponent of 10. So the log is like the 0.26, but kind of like when we were doing like pH versus concentration, if you want to get rid of the log, you can take that 0.26 and put it up there as the exponent of 10. Now, if I plug that in my calculator, I'm going to go 10 to the 0.26. So I'm going to go 10 caret 0.26, and then I get 1.82 equals, oh, we're getting closer, A minus all over 0.1. Aha, I think we're almost there. Alrighty, so now I can cross multiply and I'm done. So if I cross multiply 1.82 times 0.1, I get the concentration of A minus. A minus is 0.182. And now when I use brackets, that means concentration or molarity. So this would be moles per liter. So there we go. And that's what I'm looking for. How many moles should be added to 1 liter of the acid? And the acid's concentration was 0.1 molar. So I'm going to need 0.182 moles of my conjugate base per liter of solution. That's a lot of work, isn't it? It's pretty impressive algebra. The key was that I had to remember how to get rid of the log. So it's the log base 10. So just take that 0.26 or whatever you would have gotten and use it as your exponent of 10. Okay, so moving on then. I want 0.182 moles per liter. Next problem, number 3. Calculate the moles of that solid conjugate base that should be added to 100 milliliters of the weak acid. Well, what if we don't want to make a whole liter? I'm just going to make 100 milliliters. So, the easiest way to set this up might just be to use some simple ratios. So I just calculated 0.182 moles of that base per liter. Well, what if I want to know moles in just 100 milliliters? Or I could say 0.1 liters. Or you could have used like 1,000 milliliters as a liter and then 100 milliliters for my solution. And so now I can simplify again. And I should get 0.0182 moles of A minus in 100 milliliters of my acid. So I'm only going to make 100 milliliters of solution. Okay, well now I'm going to use 100 milliliters of the acid, but the conjugate base here is going to be the acetate ion, and it's coming from a solid. And so in 4, I'm going to want to mass that solid. Calculate the mass of the solid conjugate base that should be added to 100 milliliters of the weak acid solution. Piece of cake here, right? So now I'm going to say I want 0.0182 moles. And I'm going to go back to the materials list just to make sure I get the formula right. So we are using the acetate buffer, and the conjugate base is going to be the acetate ion, and it's coming from sodium acetate. Sodium acetate. O2. And it does kind of tell you in the materials list that it's a hydrate. It's a trihydrate. Remember way back in the day, this was like first semester, where we talked a little bit about hydrates. They're super common. It's just that often ionic solids have water molecules kind of embedded in their crystal structure. Why do we care? Well, because when I want the molar mass, I need to include the mass of those water molecules. Now, the nice thing is that they give me the molar mass also in the materials list. So I'm going to cancel moles, and I want this in grams. So in the materials list, they tell me that this is 136 grams per 1 mole. It feels like forever since we did a mole calculation. All right, so now I'm going to plug this in my calculator. 0.0182 times 136 grams. And aha, I get something that I could actually measure. Grams. That was a lot of work for one number, huh? I'm going to use 2.48 grams of the solid sodium acetate. So now I can finally describe how to make this buffer, which will hopefully have a pH of 5. Write a description of the procedure that you will follow. So I'm going to say step 1. Measure 2.48 grams of solid sodium acetate. That's going to be the source of my conjugate base. Now we want to make the solution as accurate as possible, so I'm going to say in step 3, add the solid to a 100 milliliter volumetric flask. Those are those volumetric flasks that are like really skinny, and then they have like the bulb at the bottom, and there's only one mark on them. So it's only meant to be used for exactly 100 milliliters of solution. Now, obviously, they come in different sizes depending on what volume of solution you intend to produce. Alrighty, then, whoops, I wrote a 3 here. Hello, that was step 2. Step 3. Now I'm going to add acetic acid, which will be 0.1 molar until I hit 100 milliliters total volume. And then we'll just say swirl or stir to dissolve. Swirl to dissolve. So making a buffer, it is like a physical mixture of an acid and its conjugate base, which I think is kind of good to like actually make a buffer, then see a buffer form. That, yep, I have to measure in a certain amount of the acid and a certain amount of the conjugate base. Here, our conjugate base is going to be a solid. And then once we've got this procedure, we should probably go in the lab and try it and see how close we get to our target pH of 5.